For Lab 5, I chose the Falling Slinky video in order to model the motion of a stretched slinky dropped from static equilibrium. The main goal was to model how the bottom of the slinky stays stationary when dropped. In this lab, Newton's second law, as seen with the velocity update formula on the left, is helpful in showing the relationship between the change in the slinky's motion and the overall net force, which is the sum of all the forces. I found the continuation video of the provided video on Canvas and decided to take a different approach. I coded a hypothetical model of how the slinky should behave and then used the video in Tracker to compare with my GlowScript code model. On the second graph in the top right over here, you can see that the bottom of the slinky is relatively stable until around 0.66 seconds, where it then began to plunge downwards. As I mentioned, I coded in GlowScript before my tracker experiment, so I had to estimate some values, such as assuming a standard mass of 1 kilogram for the slinky and testing a proportionality constant of 60. The hypothetical proportionality constant models the drag force acting on the slinky. Additionally, I began at a standard time of t equals 0 seconds. The net force is the sum of all the forces. To find the net force, the GlowScript code contains 2 while loops that show the 2 main forces, gravity and drag. The first while loop, on the left, shows F net equal to the force of gravity and the tension force acting from the motionless top of the slinky. And the second while loop, as shown on the right, shows the F net while the slinky is in motion equal to the force of gravity plus the drag force. Gravity is modeled as negative mass times gravity, while gravity, with gravity being 9.8 meters per second squared. The drag force is in the positive y-hat direction since it is opposing the gravitational force, in the negative y-hat direction. Taking a look at GlowScript, you can see that it models the same track as my tracker video output. The base of the slinky is constant until around 1.5 seconds here, which is where I coded the while loop originally, and then it takes a sharp decline as the entire slinky drops to the ground. One small edit to note is that the force of gravity arrow is shown pointing down the entire time, the magenta arrow, and the drag arrow pops up towards the end as the slinky falls, the blue arrow. But before the drag arrow appears, there should have been a yellow tension force arrow. It would have been pointing up until that point as the bottom of the slinky was motionless. Here's a close-up of the model graphs from GlowScript, along with the actual results graphing the point particle system from Tracker. So you can see I used different time values, but they show the same direction in the model. So ultimately, the bottom of the slinky is motionless because of the upwards tension force balancing out the downwards force of gravity. The force of gravity, in a way, takes over while the slinky is fully compressed and begins to fall downwards after the top of the slinky crashes down into the bottom of the slinky.